Okay, so for today we're going to be talking about atomic spectra, woo, because it helps us with light. So what atomic spectra are there these pictures here? I'm sure you've seen them before in chemistry class or whatever. So what this is your color spectrum here, your Roy G. Biv. And what it is each metal, well, material, but we're just going to say metal because these are all metals, like copper, will give off certain colors when it's treated in a certain way. So like when it's heated to a very high temperature. And different metals give off different combinations of color. Now what you should notice is it'll only give off these wavelengths in particular. It won't give off this section or anything like that. It's just three specific colors, and those will add together to make its own type of color. Now one thing they use this for in the real world is to identify an unknown. So if I have some mystery metal that's right here, what I would do is I would compare it against some other metals that I do know, like, for example, strontium. Now I know that this metal is strontium. This is one of the big ways that they identify chemicals in the real world, by doing a spectra measurement or using a spectrometer. Okay, or a chromatographer. It's very similar. Now, this works in two ways, because you could have the metal or material, this is hydrogen, it's not a metal, but you get the idea. You could have it give off, which is called the emission spectrum, or you could have it absorb, which is the, get this, absorption spectrum. So you will notice that these two things are basically opposites of each other. Okay, all these colors can fit into the other one where this has holes. Okay, now the reason for this is because if you give the metal energy, what will happen is it will give off the light. It'll only give off these certain ones. But if you shine light into the metal, the reverse will happen, and it will absorb the energy from these places only. Now, this energy, for example, at this level, is useless to it. So it will just bounce off, because there is nothing that it can do with that energy. So these are the particular places, the particular amounts of energy that it can use. Now I'm saying energy instead of wavelength, because you need to remember that each wavelength, because constant speed of light, has a particular frequency, and each frequency can generate a particular amount of energy using our fancy pants formulas here. Or you can do, let's see, what'll be hc over f. Whoop. Sorry, hc over lambda. Okay, so you have that, where each wavelength corresponds to a particular amount of energy. Now, this is done because each type of atom has a certain arrangement of electrons. We're going to talk about hydrogen. This is hydrogen. Hydrogen's the most popular for this kind of stuff. Now, just like everything else, electrons like to be in the lowest state possible. That's why you don't have floating things inside of your room. Now, if you give the electron energy and you give it a kick, what will happen is it will jump up. And it will jump up to some level depending on how much energy it is. This axis right here shows you the energy at different places. You will notice that all these values are negative, because when you're super duper far away, that is called the zero level. So if it goes from this level, the first level, to the third level, it is going to go from negative 13.6 to negative 1.2. So this will take 12.1 units of energy, and it's in the electron volts, which is a unit of energy. We're not going to worry too much about that yet, but whatever. So it takes 12.1 electron volts to go from here to there. If you gave it not 12.1 electron volts, but 11.5 electron volts, it would not care about 11.5 electron volts because it can't do anything with 11.5 electron volts. So for this stuff, you either get it all the way to from one level to another level, or nothing. So it's an all or nothing thing here. So, you know, for example, 10 electron volts will not be, 10 is quite enough. But if you give it 8, it will not be enough to jump, so it won't even absorb the 8. Now, let's say we got your electron up to here. What will happen is it will fall back down. It'll fall back down. It'll release the energy, 12.1 electron volts. Now, the energy it releases is going to be in the form of a photon. Right? A photon, it makes up light, and the photon will have a particular wavelength, the wavelength with this much energy, and that's the color in the spectrum. That's why you have particular colors, because you have a particular distance here, a particular distance there, here, there. All these distances are very particular. So you can only have your electrons dropping very particular distances. Since your electrons can only drop very particular distances, you can only release energy in very particular amounts, because the photons will only have the energy that matches the drop of the electron. So that's what's happening. That's why you have those distinct lines there. All right. Now, these lines have different wavelengths and different series. So for hydrogen, like we're doing now, you have the Lyman series, which goes down to level 1, and you have the Balmer series, which goes down to level 2, and the Paschen series, the Paschen, which goes down to level 3. The Balmer series is by far the most popular of the group here, because this is the colors you can see. These ones have too much energy, they're going to be ultraviolet, and these ones have not enough, they're going to be infrared. So, that's why these ones are the popular ones, you know, except for this one. This one right here. This one right here is not quite visible, but you get the idea. So these ones give hydrogen its color. By color, I mean its emission color. When you see neon lights, every neon light you've ever seen works the same way. Neon is only actually in red. If you ever have seen a yellow, orangish neon light, that is going to be actually hydrogen. Or sorry, I mean not hydrogen, helium. That is the color that you see from them, and so on and so forth. If you see blue, I think it's krypton. But I'd have to remember. I don't remember that off the top of my head. But anyways, this is how the light breaks apart. You can also see this in fluorescent lights. If you have the lights in, you know, offices or the school, for example, they use mercury vapor in doing the same type of strategy. They bounce electrons up and down, and they release certain colors of light, which gives it a more yellowish hue to it, as opposed to outdoor light, which is much more white, because the sun doesn't do this. The sun emits white light, which is every single color everywhere.